Okay, and Dr. Liu is a professor in civil and environment engineering in University of Michigan, and he's also a research professor in University of Michigan Transportation Research Institute. We call it AMTRI. So it's one of the most famous connected vehicle safety pilot deployment institute. And before he joined University of Michigan, he was associate professor at the University of Minnesota since 2005. Right?
Yeah.
And Dr. Liu got his PhD from University of Wisconsin Medicine, and also his bachelor degrees in automotive engineering in Tsinghua University in China. So his research areas include traffic signal operations and network modeling, traffic flow theory, so a lot of applications in transportation areas. So today his topic will be how to manage and measure oversaturated traffic conditions, which is a very challenging problem in existing transportation world. Okay, so let's welcome Dr. Liu's talk. Okay.
Thank you, Jing. Thank you for the invitation. Glad to be here. It's snow day, but it's snow day in Michigan also, so I don't have a problem with snow. So like Jing mentioned, what I'm going to talk about is managing oversaturated material, and this is a particularly challenging problem in transportation. We have lots of models has been developed in traffic signal and traffic signal control, but not so much on oversaturated conditions, and because of the difficulty, which I'm going to mention later on. So let me start with sort of like a history quiz on traffic signal. So how many of you know that the green, yellow, red signal, how long has been in the field?
100 years. Yeah, a lot of years.
A lot of years, yeah. So the first green, yellow, red signal was invented by William Porter and instrumented at Detroit in 1920. So so the traffic signal has been there for roughly about 100 years. But if you see in terms of even at the current state of the practice, how we usually measure the traffic signal performance, how we know whether the signal performing good or bad, or it's okay, or do we need some work on it. And it still is very, very much manual, very rudimentary. And I think most of you, if you're in the transportation class, you probably know some sort of counter. We usually, at the intersection, we use this J-mark counter to count different turning movement, and that's very much manual. And yet, if you look at it in terms of what's going on in the traffic signal systems, there's a lot of data is available, but it's not being utilized and being collected. So I'm showing you this National Traffic Signal Report Card, and every 5 years, Federal Highway has this report card to tell you what's the current state of our traffic signal systems. There are roughly about 300,000 traffic lights in the US, and we want to know how they perform. And there's one particular category I want to mention to you is this, this traffic monitoring and data collection. And this is one is in 2007, another one is 2012 in terms of how much data we collect, how we monitor traffic signal system, and we consistently being ranked at F, meaning we don't really do much around it. What is also pathetic about this form is we don't, these grade, let's say this is D in 2007, actually getting better D plus in 2012. And if you ask these people who really developed this report card, you ask them what's the methodology to give you a rate of D or D plus, and not much. What they do is they send out surveys to traffic signal agencies and let the traffic engineer rank themselves. So they ask you, how do you feel about your traffic light? If you give a grade C or give a grade D, and they take an average of that. None of these things is objective, meaning it's all subjective evaluation and survey about the traffic signal status. And so this also tells you there's a great need that we need some system in place to help us to measure the traffic signal performance and automatically to reduce the manual effort. So my talk today is really three portions. One is how we really measure the performance, how we know the traffic signal is working good or bad, or it's okay, do we need some work on it or not. The second thing related with this is this particular difficult problem of oversaturated traffic signal, how we really manage oversaturation on urban arterials. And then before we do that, I want to do quantifying oversaturation. Is the oversaturation severe? In what situation, in what condition the saturation occurs? And then if we can quantify that, then how we going to manage this? So then I'm going to show you some of the results we have. So I'm going to start with this performance measure, and I say performance measure using the so-called high resolution data. Really, if I say this high resolution data, it's not really that high in terms of the resolution. But compare with the state of the practice in terms of the data we use, and this is really high resolution. And I'm going to tell you what I mean by that. So this is a project I did at the University of Minnesota when I was a faculty member there. And the name of the project we call Smart Signal System, and is representing systematic monitoring of arterial road traffic signals. And this is a serial project which is sponsored by US DOT, Minnesota DOT at the time, and then part of the National Academy of Science and PRB. When I started at the University of Minnesota, I was trying to find a niche topic. Really, at the time when I started at the University of Minnesota, there's this famous traffic flow professor, Panos Maklopoulos, and he's still there, and he's sort of half retired. He's really well known in the field. He did a lot of things related with traffic flow, and his paper in 1980 is still making a lot of impact. So I was the person hired to replace him. I was really trying to find some topic really unique that I can make a contribution. So one of the things I was thinking about, and that was back to my postdoc time, is to collect data at traffic signals. And so I was trying, even during my postdoc years, working with Caltrans in terms of data collection, and wasn't really that successful. So when I started at University of Minnesota, I asked the Center for Transportation Studies director to help me to connect with these traffic signal engineers at the agency. So I met with several of these traffic signal engineers, City of Minneapolis, Hennepin County traffic engineer, State DOT's traffic engineer. For the most part, the answer I got is no. You can't touch our traffic signal system. There's so much liability there. You can't open up the cabinet. We can't do anything about it. So at the time, I also have startup money, so I don't need the money. I just need the open access to the traffic signal cabinet. So finally, I was able to convince Hennepin County, their transportation department director, to allow me to instrument on their road. And he was kind enough to also give me a spare cabinet so that I can put in my lab and do the testing, and do the evaluation in my lab also before I can put it into the field. So we developed this data collection system which can automatically collect the so-called high resolution data at the traffic signal location. We started the development in 2005, and the first instrumentation was in 2008, and on one of the Hennepin County roads called France Avenue. And this is France Avenue's first instrumentation. So this is the first generation of the data collection system we developed. And if you can see, this is just a really so-called industrial PC. It's $400 at the time. And then this industrial PC has a data acquisition card from National Instrument. And then, and on top of that, there's this what we call terminal box, which separates our device, this computer, with the rest of the cabinet. So if you're familiar with the traffic signal cabinet, this is the traffic signal controller, And this is the back panel, which is connect to all of these loop detectors in the field, give you the vehicle actuation. And these are the signal load, which connect to the traffic light, signal head, so give you the indication of green, red, yellow. So, and data acquisition card can only have the input functionality, meaning we receive data from the traffic signal cabinet. We don't output any command. So we don't control anything. We just sort of like a listening device, archive, everything happens at the traffic signal, but don't do anything about it. So, and that's initially what we would ask. We can't touch controller. So controller controls the traffic light, we can't touch it. So what we were able to do is to sniff into the pins of these vehicle detectors. So for each of the detector, we have a hot wire snip into it, and for each of the signal head, we have a hot wire snip into it. And so every signal phase change, we get a signal. So we timestamp that signal change. Every vehicle detector actuation, we get a signal. So if this is the detector, when vehicle arrives, we basically receive two timestamp data. One is when the vehicle touched the detector, actuation, and then when the vehicle leave the detector, which is the detector deactuation. These two events are timestamped. So that's all we can get, and that's everything happens. When the pedestrian pushes the button, we receive that signal too. So every event occurs at the intersection, we timestamp that, and that's what we call high resolution data. So this is the first generation we developed. We first developed in the lab, and then in 2007, late 2007 and early 2008, we put it into the field. At the very beginning, it was 11 intersections. And this is the second generation. So later on, when the project was successful, was matured, and then we started to work on our data collection box. Start from this big, very clunky computer industrial PC. We developed a very simple data collection box, like a small book, this size. And then instead of sniffing into the pins of the back panel, we now connect to the controller. So now, because we show to them, they do no harm to your controller cabinet. So now they allow us to connect directly to these harnesses within the controller, within the signal controller. So what happens is they usually have these harnesses connect to the controller. We have a Y harness, which is this is our Y harness. So there's a group of wires coming out directly connect to our data collection box. So in this case, we don't need to manually tap into the pins. We just do plug and play. We can collect the data. So this is for the NEMA TS1 type of cabinet, and for the newer type of cabinet, we don't even need to connect to the controller. We simply tap into the SDLC port so that we can listen to the messages being transmitted between the controllers and also the signal head, and then we know we can collect the same type of data also.
Do you use a DCIP to talk to the controller?
We actually, yes, we do. So we just basically tap into the SDLC and then listening to
SDLC.
Yeah.
Okay.
Yeah.
How about the 2070 controller?
Okay, I'm going to show you that. Okay.
Yeah.
So this is actually very recent. This is Wednesday this week. So after the project was successful, later on there was a startup company started by University of Minnesota to commercialize this, and two of my students are still working for the company right now, and after they graduate. And this is one of my students, and actually majority of the work I talk about today is his work, so I just have the pleasure to talk about it. And so this is at City of Pasadena. You can see all the sunshine and on Wednesday this week, and with some of the staffs over there, city staff over there after the installation. So this is 170 or 2070 controller, and instead of these ABCD harnesses, if you're familiar with traffic signal world, then this becomes this this C1 files. So what we do is we have the same wire harness, which is this is their original C1 file. Connect to that controller. What we do, we have both male and female pads, so that one side connect to the original, the other one connect to the controller, and split the wires to our data collection box. It's extremely simple. The board itself can be developed by these electrical engineers probably in a week or so. It's very simple data collection device. So if you look at the data, this is the first generation data. It doesn't look like that right now, but essentially what the data we collected is what I mentioned, that every detector when it's on, with actuated, we timestamp it, and when it's off, we timestamp that. When every traffic light is on, we timestamp that, and that's basically what we have, and this also called event-based data. And right now there are further development on these loop detector data. They can even look at it in terms of the signature of the loops, so they have much higher resolution than what we have here. But even just with these event-based data, we can do a lot of things already. So I start the talk with performance measures. So the most important thing for traffic signal at the intersection level, is to look at it in terms of Q length for each approach. If you know the Q length for the approach, then you essentially can derive the delay, number of stops, and level of service, and all sorts of performance measure can be derived from the Q length measure. So the first question we tackle is how we're going to evaluate the Q length at the intersection. And Q length measurement is also a traditional challenging problem in traffic flow theory. And most of the Q length measurement method in the previous literature is to use the so-called input-output approach, which is very easy to understand. So if you have a detector somehow upstream, if you have a detector somehow downstream, and then you measure the input, you measure the output, essentially you know the number of cars inside. And that's the essence of it. But when you have a long queue, you have